the entire new topic. So these are the direct integration methods. Uh, Mostly it is used for the analysis of structural dynamic problems. So in this method, we are going to learn four different methods. The first method is central difference method. Then there is a Hobart method, Newmark method, and Wilson theta method. Most of the methods they have a same pattern. Only thing is there are few changes, like constants are changed. Sometimes the equations are changed. Okay. So today we will start with the central difference method. Okay. So let me start the PPT. So this time I have prepared a PPT. Uh, so let us start. Okay. So in the central difference method, what happens is, or in the structural dynamic problem, what happens is we end up with this equation. Okay, that is k into displacement into c into the velocity and mass matrix into a acceleration. Okay, so this u stands for the displacement. Okay, this u prime, so this u dot you are seeing on the screen, it is called as u prime. So this represents the velocity, and u double prime, or you can say u double dot, it represents the acceleration. Okay. So this k is nothing but your stiffness matrix.
सर सर
Yeah.
दिख नहीं रहा है सेकंड चेंज
Sorry.
नहीं हुआ स्लाइड
Sorry.
सर चेंज नहीं हुआ है स्लाइड
पीपीटी नहीं दिख रहा है सर.
PPT नहीं दिख रहा है, that is strange. Okay, let me stop the sharing and let me share once again. Okay. uh, I'll share the entire screen, that will be better. Okay, so now I hope it is visible to everybody.
Yes, sir.
Okay, so what I was talking about is, uh, we have a equilibrium equation in dynamics. So this equilibrium equation is k into u plus c into u prime and plus m into u prime. So you can call this as u dot and u double dot. So where this u is nothing but your unknown displacement, u dot is nothing but the unknown velocity, and u double dot or u double prime is called as the acceleration. Okay, the matrices which are associated with this are, so displacement is associated with the stiffness matrix k, the velocity, that is u dot, is related with the damping matrix c, and the mass matrix m is related with the acceleration vector u double dot or u double prime. Okay, and r is the load vector. Okay, so these are the standard terminologies which are coming from the structural dynamics. Okay, so now what happens is, in the structural dynamic problems, we have loading which is depending on the timing. So as the timing changes, so the total duration of the analysis is, let us say, t. So t can be 8 seconds or maybe 10 seconds. So depending on the type of the problem, this r value or the load vector, it is going to change. So when time is equal to 1 second, r will be something different. When time is equal to 2 second, r will be something different. Okay, so this is not constant. So this r, sometimes it is constant, sometimes it is not constant. Okay, but the effect of this is what you are going to get, a deformation which is something different. Okay, so just for sake of understanding, if I draw a simple cantilever over here. Okay, so this is my cantilever, and this, there is a load of p which is acting over here. Okay, now let us say I am doing a dynamic analysis for a period of, let us say, t is equal to 10 seconds. Okay, so if my period is equal to 10 seconds, in that case what will happen, for example, say this p is constant. Okay, so it is not changing with time. So if I draw a time frame, okay, so if I draw a time frame, this is my time frame, this is 1 second, this is 2, this is 3, this is 4, this is 5. and so on. Okay, so this is my, let us say, time frame. This is 6, 7, 8, 9 and 10. Okay, so this is my time frame. Okay, so what is going to happen in the dynamic problem, due to many factors, okay, that I'm not going to going in details. Let us say I'm focusing on this point. So this is my free end. Okay, so this free end, what it is going to happen, it is going to oscillate. Okay, so sometimes it is going down, sometimes it is going up. So what will happen, you will have a deformed shape something like this, and after some time deformed shape will go something like this. Okay, so what will happen if I draw a displacement over here? Okay, so let us say this side we have a delta. Okay, so this is positive and this is negative. So when time is equal to 1, you will get a displacement which is somewhere over here. When time is equal to 2, you will get displacement somewhere over here. Time is equal to 3 here, time is equal to 4 here, time is equal to 5 here, 6, 7, 8, 9 and 10. So what is going to happen, you are going to get a deformed shape something like this. This is what we call it as a response of a structure. So slowly you can say it is decaying. Okay, so we have to do the analysis such that we need to find out the acceleration, velocity and the displacement at a given point. So in this case there is only one point. So if I take a structure something like truss, okay, so let us say this is my truss. Okay, so we have a deformed we have support over here. So now I will say you will have 3 points. Okay, so these 3 points, they are going to behave in a different way. So this may go down, at the same time this may go up. Okay, so if I draw a curve which is something like this for displacement for these 3 points, they will not overlap each other, they will have some different responses. Okay, so we have to understand that and then we have to solve it. So ultimately in dynamics problem, what you are going to get, you are going to get a equation, equilibrium equation. So your equilibrium equation is what, k into u, that is k into delta is equal to, let us say, f. Okay, this is the static case. Okay, but in case of dynamic, you have k into u plus c into u prime and plus m into u double prime is equal to, let us say, r. Okay, so these two terms, they are going to increase as far as this part is concerned. Now the thing is like this, this is your unknown, this is also unknown and this is also unknown. So you don't know what is u, you don't know what is u double dot, you don't know what is u double dot. Okay, u dot and u dot, everything is unknown. So only known factor is your k, the c value and the m value, and there is a r value. So this r value is also changing with time. So these 4 components are known to us, and then how to solve this. So usually what happens is this equation, okay, so this entire equation will be converted somehow into a simple equation, that is u in k into u is equal to f. So this can be solved using Gauss elimination method or any other method which we have seen for the solution of system of linear equation. Okay, so let us try and understand this method today. Today we will see the central difference method to analyze this particular problem. Okay, so is it clear to everybody? Any questions as far as this part is concerned? Please respond. Yes, students. Okay.
Yes, sir.
Okay. So in the central difference method or any other method which we are going to see in this particular topic, there are 2 parts of the analysis. The very first part is the initial calculations. Okay, so initial calculations has to be done only once, okay, before solving the problem. Now in the initial calculation, the very first step over here is you should know what is the stiffness matrix, what is the damping matrix. So I think this is mass matrix is M and this is damping matrix is C. Okay, so I have mistakenly written over here. So you should know what is this mass matrix and what is this damping matrix C. So this can be found out using the basic properties of the material. So this part is usually given in the numerical because This is a computational technique subject, not the dynamic subject. Okay, so when you are solving the actual dynamic problem, in that case you have to find out what is the K matrix, what is the mass matrix, and what is the damping matrix. But as far as this subject is concerned, these matrices will be given to you. Okay, now in the second step, you have to find out what are the initial conditions, like when your problem is about to start. At that point, what is the situation of the unknown displacement, what is the situation of the acceleration, what is the situation of the velocity. Okay, so the initially what happens is your t is 0. Okay, so when t is equal to 0, what is the value of u when t is equal to 0, what is the value of u double dot when t is equal to 0, and what is the value of u dot at t is equal to 0. So this is what, this is displacement, this is acceleration, and this is nothing but your velocity. Okay, so these three values, initial values of acceleration, velocity, and the displacement, will also be given to you while solving the numerical. Okay, now the actual calculation starts from the step number 3. So in the central difference method, we have to find out 4 different integration constants. So these 4 integration constants are A0, okay, then A1, then A2, and then A3. So A0 can be calculated as 1 divided by delta t square. Okay, so delta t means what? Let us say I want to find out the response of the structure for a period of time, let us say 10 seconds. So I am going to divide this time into different several parts. Okay, so delta t we have to calculate, let us say capital T divided by, let us say 10. Okay, or it can be 100 also. So it will be given to you. So it is a small increment of time over which you have to find out the response of the structure. So delta t will be given to you. So definitely you can calculate A0. Correspondingly, you can also calculate A1. A2 also can be calculated as 2 times A0, and A3 can be calculated as 1 upon A2. Okay, now in the fourth step, we have to generate the effective stiffness matrix. Okay, so remember we have a equation of dynamics like K into U plus this C into U dot plus M into U double dot is equal to R. So this is the equation. So now this has to be converted into a simpler form. So to calculate that simpler form, what we are generating the effective mass matrix. Okay, so the effective mass matrix can be calculated as, this is M and there is a cap over here, so it can be calculated as A0 into M plus A1 into C, out of which A0 and A1, they are the integration constant which we have already calculated, and M and C, they will be given to you. Okay, now in this particular step we are starting with the t is equal to 0. Okay, so we have to find out what is the velocity or what is the displacement at t is equal to minus delta t. So this is required only once, because it is used in the further calculations. Okay, so here you can see this is the displacement at t is equal to minus delta t. Okay, so t is 0 and delta t can be any value which we will be calculating. So this can be calculated very simple expression, that is u at t when t is equal to 0 minus delta t into the velocity at t is equal to 0 into plus a3 into what is the acceleration, that is u prime at t is equal to 0. Okay, so once this value is known to you, your first step is done. So that is your initial calculations are done. So this has to be done only once. Then we have to go for the stepwise calculations which are there in the third step. Okay, sorry, in the second step. Now this is the every step calculations. Okay, so let us say I want to calculate, so we already have t is equal to 0. So now I am working on delta t. So delta t can be, let us say 1 second for example. Okay, so delta t is, let us say 1 second. So in that case I have to calculate what is the effective load vector at t is equal to t. So at this time, that is at t is equal to 1 second, what is the effective load vector r that I am calculating. Okay, so effective load vector r can be calculated as, firstly, what is the load at this time is equal to 1. So remember, your load is continuously changing or it can be a constant. depending on the type of the problem. So whatever value of load is there at that point of problem has to be taken over here. Then we have K matrix, then we have M matrix. So M has to be multiplied with A2, and this has to be multiplied with what is the displacement at t is equal to 1 second. Okay, also not 1 second, t is equal to 0 second. So here this will be 0. Here also this will be 0. Okay, so now A0 into M plus A1 into C, and here you see, here you are getting something like t minus delta t. So here, so t will be now minus 1 second. Okay, so this we have already calculated. So accordingly we can get the effective load vector. So this effective load vector will get transferred over here. Effective mass matrix, this we have already calculated. Okay, so using this, so what we have done basically, so K into U plus C into U dot plus M into U double dot is equals to R. So now this equation is now converted into a simpler equation, that is effective mass matrix. This is effective load vector, and this is the displacement. So now this will become t is equal to 1 second. Okay, so this becomes 1 second. So now what you can do is you can calculate what is the displacement at t is equal to 1 second by simply solving this equation using Gauss elimination method or any other method, and you can get the unknown displacement at t is equal to 1 second. Similarly, you can get the velocity at t is equal to 1 second. So initial value of t is 0, delta t is 1 second. So this equation becomes 1 second. Okay, so what is the velocity at 1 second? So this can be calculated as A1 into, this is the displacement at 1 second, and this is the displacement at 0 seconds. Okay, so naturally we can get the velocity at 1 second, and here you can get what is the acceleration at 1 second. So this will be -1, this will be 0, and this will be +1. Okay, so all you have to do is substitute the values, and then you can get the acceleration at t is equal to 1 second. So this is the stepwise calculation which we have to follow for first step. For the next step, you have to follow the same thing. Okay, so in place of now t, initially we have calculated delta t, so now it will become 2 times delta t. So 2 times delta t will become 2 seconds. So same expression will be followed. Only thing is now here initially it was t, so this will become now delta t. If this is t, this will become delta t. This is t minus delta t, so this will become only simply t. This is t plus 2 delta t will come over here. So like that, all the expression, they will be increased by a delta t. Okay, and correspondingly you have to find out the the response of the structure. So when I say response of the structure, this means you have to find out the velocity, acceleration, and the unknown displacements. Okay, so let us try and solve one simple problem so that the situation or the problems on methodology can be clear to you. Okay, so this is a problem which is given to you. So this is a 4x4 matrix. Okay, so you can see this is a very big problem. It's a 4x4 matrix. So this is the u term. So this is the displacement term. So definitely this matrix is nothing but your k term. Okay, plus this is a u double dot term. So if this is u double dot term, this means you have M matrix, and this is equals to R. Okay, so this is given to you. Now where is your C? Okay, C is not given to you. Okay, so what you can do is you can assume the value of C, and in this particular case C is totally absent, so your C value can be considered as 0. Now what it says that you have to find out the response of the structure in, let us say, 10 step. Okay, so I am using only 10 step for a period of t is equal to 7 seconds. Okay, and the delta t, I am considering this as capital T divided by 50, and the initial vectors. So here you see, when t is equal to 0 and when t is equal to 0, the velocity is 0 as well as the displacement is 0. So this is the velocity, so and this is the displacement. Okay, so now we have to find out what is the acceleration at t is equal to 0. So this is not yet known to us. Okay, so this is the situation right now. What is not known? C is not known. Okay, and what is the acceleration at t is equal to 0? This is not known. So what we can do is we can solve this. So like I said, we can solve this expression. Okay, so here this is the generalized expression of dynamics. So your k value is known, the velocity values are known, your c value I am assuming this as 0, the velocity is known, acceleration is not known but mass is known, and r is also known. Okay. So now what you can do is you can substitute the value. So you can see the k value I have written over here, c value I have written over here, and the mass value I have written over here, and here you have the displacements, here you have the velocities, and here you have the acceleration. Okay, so all the values are known to us. Okay, so now we can substitute the values. So in the problem what is given to you, that is the displacement, that is u, is 0 at t is equal to 0. At the same time the velocity is also 0 at t is equal to 0. Okay, so this is the expression which is written, this is the expression at t is equal to 0, that is time is equal to 0. So if you solve this, so this entire term, this will be 0, this will be 0, and what is remaining, only this part is remaining. Okay, so what you can do is you can solve this so that you can get the acceleration, that is u double prime at t is equal to 0. So this will be now known to you. Okay, so these values, so since this is a 4x4 matrix, so you will get the 4 values. Okay, so now we can start our problem, but before starting the problem we have to find out the coefficients, integration constants. So delta t, so in the problem the delta t is given to you as capital T by 50. So capital T is 7, so divided by 50, so delta t comes out to be 0.14, and correspondingly we can calculate now a0, a1, a2, because all these are simple equations, and accordingly now we can get a0 as 51.02, a1 as 3.57, a2 as 102.04, and a3 as 0.0098. Okay, then we have to calculate the effective mass matrix M. So M cap, so already the expression is given to you. So out of this, a1 is known, a0 is known, m is also known, and c is also known. C is already 0. Okay, so since c is already 0, you can get the effective mass matrix as the a0 into mass matrix only. So you are going to get a very simple expression over here. So this is the effective mass matrix, 204, 153, 102, and 51. Okay, so this is the effective mass matrix. Then if you remember correctly, we are solving, we know the response at t is equal to 0. We are interested what is the response at t is equal to delta t, t is equal to 2 times delta t, t is equal to 3 times delta t. So for this we should know what is the displacement at t is equal to minus delta t, that is one step prior. So this has to be calculated over here. So this value u at minus delta t, so here if you substitute the values, so here, the values at u is equal to t is equal at u at t is equal to 0, they are already known to you, and u velocity, that is u dot, is already given to you, and u double dot is already given to you, right now we have calculated this value. Okay, so if you use this, so what you are going to get, what is the displacement at t is equal to minus delta t. So we can easily find out what is the displacement over here, and these values are these values. Okay, so these are the initial calculations. Okay, so initial calculations are now done. So now let us try for the stepwise calculation. Okay, so now we are going for the first step. So in the first step I am going for t is equal to delta t. Okay, so for that the what is known to you, so we have t is equal to 0, we have t is equal to delta t, and before that we know what is the value of t as minus delta t. Okay, so three things are there. Okay, and we are calculating the response at this level, that is t is equal to delta t. So for that we have to calculate the effective load vector. So effective load vector r cap is nothing but what is the r at t is equal to 0. Okay, so in the numerical it is not mentioned that r is changing. Okay, so we can keep this as constant. So r value is 5, 8, 11, and 14. So this we are going to keep this as constant. Then the k matrix is over here, the mass matrix is over here, the a2 value is over here, multiplied by the displacement at t is equal to 0. So at this level, what is the displacement? So this is already given in the problem as 0. Then we have minus A0. Okay, so A0 we have calculated over here. Mass matrix I have written A1 we have calculated over here. C matrix we have assumed this as 0, so this is there. And then here is the most important part. So this is the displacement at t is equal to 0 minus delta t. So this value is nothing but coming from here. So in order to calculate the response at t is equal to delta t, you should know what is the displacement at t is equal to 0, and you should also know what is the displacement at t is equal to minus delta t. Okay, one step prior. So you just substitute the values, and what you are going to get is the effective load vector over here. So once this effective load vector is calculated, you can go ahead and you can calculate the unknown displacement at t is equal to delta t. So effective mass matrix we have already calculated 204, 153, 102 and 51 multiplied by this is completely unknown, that is the response or the displacement at t is equal to plus delta t. Effective load vector just now we have calculated, so now we can get, yes, this is the displacement at t. So this is the displacement at t is equal to plus delta t. Okay, so this is the displacement value. So now I have to calculate what is the acceleration value and what is the velocity value at that particular point of time. So for this we have the velocity term. So this is the equation which is known to us. So you can say this is the velocity at t is equal to plus delta t. This can be calculated as a1 into this is the displacement at delta t, and this is the displacement at minus delta t. Okay, so both the values are given or we already have calculated. So now we can easily substitute these values, and what we are getting is the velocity at t is equal to plus delta t, and all the points the velocities are 0. Correspondingly, now you can calculate the accelerations also. So this is the value of acceleration. So acceleration can be calculated at t is equal to delta t as u double prime, and the expression is a dot, or sorry, a0 multiplied by this is the velocity at minus delta t. You can see over here, this is the velocity at t is equal to 0, and this is the displacement at t is equal to plus delta t. So all the values are known to us. So all we have to do is substitute the values, and you can get the acceleration at t is equal to delta t. So like this, we have to follow the same process for the next step also. So in the next step, we are going for the 2 delta t. Okay. So if you refer the expression, this expression, that is the effective load vector for the earlier one. So if you refer this earlier one, so here you can see, here it was written as t is equal to 0. Here what will be happen, here also t will be 0, because the r value, it is not at all changing, it is keeping constant. Okay, and if you refer the earlier equation and this equation, this has been now changed. Okay, so if I refer back, so here you can see this was t is equal to 0, but now it is now t is equal to 0 plus delta t. So everywhere you will find 1 delta t is added. So earlier if you see, so here you see it is t is equal to 0 plus delta 0 minus delta t. So now delta t has been added over here, because of that you are getting this as 0. So all you have to do is just substitute the values respectively. So r is not going to change. So this is the displacement at delta t. So this value is already given. This is the displacement at t is equal to 0. All the values are given to you. So what you can get is the this is the effective load vector. Now this is the effective load vector at t is equal to 2 times delta t. Okay, so this is now calculated. Effective mass matrix, it is not going to change, and if you substitute these values over here, so what you are going to get, this is the displacement at 2 times delta t. So right now what we have something like say time as minus delta t, time as 0, time as delta t, and time as 2 times delta t. So this we have already calculated, this also we have calculated, this we have calculated in the step number 1. So this is the step number 2. Okay, so we are now able to find out what is the displacement at t is equal to 2 delta t. Similarly, you can calculate the velocities also. So this is the velocity. Now here, whatever expression we have used earlier, everywhere now we have to add delta t one more time. Okay. So now let me go back. 1, 2, 3. So this is the velocity term. Okay. So here you see the velocity. Here it is t equals to 0 plus delta t. Now it will be 0 plus 2 times delta t. Okay, so here you can see it is 2 plus 0 plus 2 times delta t. Here it is 0 and here it will be lesser than that. Okay, so minus delta t. So all you have to do is just increase the delta t in the second step, and you can get, now this is the velocity at 2 times delta t. Okay, similarly you can get the acceleration at t is equal to 0 plus 2 times delta t. All you have to do is, or take the earlier expression, everywhere you just add delta t one more. Okay, and what you are going to get is the acceleration. Okay, so same thing we have to repeat for step number 3 also. So I'm not going in much details. So everything remains same, only thing is now this delta t will be added in the earlier expression. Okay, and you can get this is the displacement over here, and this is the velocity over here, and this is the acceleration over here. Okay, so like this you can have the 10 step, because in the problem it is mentioned you have to solve this for 10 step. So after solving the 10 step, so what we are going to get is like this one. So while we have started the problem, t was initially 0. These values were known to us, this was given to us, and this is the displacement at minus delta t. This we have calculated just for sake of starting the calculations, and based on that we have calculated the velocities, and we have also calculated the acceleration. Okay, so this is when t is equal to 0. Okay, so now when we have solved this problem for 10 different steps, so you can get, this is the velocity, so you can say this, sorry, these are the displacement. So these are the displacement at t is equal to delta t, then this is 2 delta t, then this is 3 delta t, this is 4 delta t, 5 delta t, 6 delta t, and so on. Okay, so you can see the values, they are completely changing. For example, if you take the first point, okay, so this is my first point. So you can see this first point, if you see the values, it is vibrating. Okay, so this is the time is equal to 5 seconds, and this is time is equal to 6 to 10. Okay, so if you plot a curve, so here you can see, let us see if I draw a time curve. So this side we have time, so this is 0.01, so it will be somewhere over here. So basically you can see it is reducing, then it is going in the minus side. So this point is basically going down like this with time. Okay, as far as the second part is concerned, second part you can see second part is increasing, because here you see this is 0.02, this is 0.1, then 0.2, then 0.3, then 0.4, then here we have 0.5, 0.6. So you see, and then it has started reducing over here. Okay, after reaching 0.6 it has started reducing. So if I plot a curve, so sorry, it will be it should start from the here. Okay, so it should start from here, and then it is starting reducing like this. So you can see that the every point is behaving in a different way, and with time the deformation is continuously changing. Similarly, you can see the velocities also. So this is the chart which is showing the velocities at different time for different points. So initially all the points, they were having 0 velocities, and with the increment in time, the first point is having the increase in velocities, then it is reducing, then it has also reducing. In fact, it is going in the minus side. Okay, if you see the fourth point, so you see the velocity has increased, then suddenly it has dropped, then again it is increased, then it is dropping once again. Okay, so it depends on the type of problem. Similarly, we can have the acceleration also. So acceleration, let us say with time, so it has increased, then it has reduced, this has also reduced, and it is still reducing. Okay, so depending on the type of problem, this is going to happen. So this is how we have to solve a problem using the central difference method. Fortunately, in the examination, we never ask a 4 by 4 matrix, not even a 2 by 2 matrix, okay, because it involves a lot of calculations. So generally, we go for only 1 by 1 matrix, okay, and number of steps are also restricted because of the time constraint. So let us try and solve a problem, a simple 1 by 1 problem today itself, okay. I hope this method is clear to you, okay. Is it okay, everyone?
Yes, sir.
Okay, so shall we start? Do you anybody is having any doubt? No? Okay. So let us start the numerical now, okay. So in the numerical, let me write down the numerical first, okay. So the equation which is given to you is something like this. Let me draw this. Is my screen visible?
Yes, sir.
Yes, sir.
Okay. So my expression is something like 4 times u double dot, okay, then plus 2 times u dot plus u, okay, plus u, okay, equals to 8. So this is a simple 1 by 1 matrix, okay. So I am talking about only simply 1 by 1 matrix, okay. So now your capital T, that is the total time duration, is given to you as 1 second, okay, and we have to go for 12 steps, okay. So we have to go for 12 steps, and the delta T is given to you as capital T divided by 5, okay. So this is what is given to you, okay. At the same time, the initial condition, that is time, is equal to 0. So when your time is equal to 0, the value of u, that is the displacement at t is equal to 0, this is given to you as 0. At the same time, the velocity, that is u double dot, at t is equal to 0 is also given to you as 0, okay. So this is how you have to the problem is defined. So let us try to find out the solution of this, okay. So the earlier what we have to do is part 1, okay. So part 1 is what? Initial calculations, okay. So in the initial calculations, first thing is you have to find out what are the stiffness matrix and other things, okay. So here you already this values is given to you. So your mass matrix is 4, okay. Then your C damping matrix is 2, and your stiffness matrix is 1, because here you see this is 1 is there, okay. And your R matrix, okay, so R matrix is given to you as 8, okay. Now at t is equal to 0, okay, what is known to you? The velocity or the displacement. So displacement is known to you, and the velocity is also known to you, but we don't know what is the acceleration, okay. So this is known to us. So what we are going to do is, first thing is we have to calculate what is the acceleration at t is equal to 0, okay. So what we are going to do is we will rewrite this expression for t is equal to 0. So when t is equal to 0, so this is nothing but 4, okay. The velocity or the acceleration over here at t is equal to 0, this is not known to me, fine, no issue. Then we have this matrix 2, the velocity at t is equal to 0, so this is 0, okay. So this is this one, okay, plus 1 into the displacement. So displacement is already 0 at t is equal to 0, so this is already known to us. This is equal to R. So R is nothing but your 8, okay. So what is going to happen? This will be cancelled, this will be cancelled, and what you are going to get as a result of this as u double dot, that is the velocity, or that is the acceleration at t is equal to 0, as 4 by 8, it is nothing but 2. So as a result of this value we have calculated as 2. So in the initial calculations, now we know what is the what is the displacement, what is the velocity, and what is the acceleration at t is equal to 0. And all these mass matrix, damping matrix, stiffness matrix, and load vector, they are already known to us. Okay, so this completes the first portion of the initial calculation. Is it clear to everybody? इसमें किसी को कुछ डाउट है क्या? Please, somebody, or shall I proceed further? Okay, fine. Now in the second step of the part 1, we have to calculate the integration constants. Okay, so integration constants, mainly it is delta t. Okay, so delta t in the numerical, it is given to you as capital T by 5. So capital T is given to you as 1 seconds divided by 5, isn't it? It is, I think it is 1 second. Yeah, 1 second. So this is capital T is 1 by 5. So this is going to become delta t as 0.2 is the time increment. Okay, then we have to calculate the integration constants, that is a0, okay, a1, a2, and a3. Okay, so a0 is 1 upon delta t square. Okay, a0 is 1 upon delta t square, and a1 is 1 upon 2 times delta t, a2 is 2 times a0, and a3 is 1 divided by a2. So can someone tell me these values, please? Constants, integration constants. Bata. Yes, anybody? A0?
25.
25. Okay. What about a1?
2.5.
Okay. a2? Think it is 50. 2 times this.
Yes, sir.
And a3? 1 upon 50.
0.02.
0.02. Okay, so all the integration constants are now available with me. So now I have to calculate the effective mass matrix. Okay, so let me calculate over here. Okay, so I am going to calculate now effective mass matrix M. Okay, so this effective mass matrix M now can be calculated by expression, that is a0 into M plus a1 into C. Okay, so this effective mass matrix M is a0 is 25 into your mass matrix. Okay, so if you see, your mass matrix is nothing but 4 value. Okay, so this effective mass matrix is written over here. Okay, so this mass matrix comes out to be 4. Your a1 is 2.5, and your C matrix, that is the damping matrix, is nothing but 2. So can someone tell me this effective mass matrix M? 25 into 100 plus 5, 105, is it correct?
Yes.
बराबर है?
Yes, sir.
Yes, sir.
Okay, so this is the effective mass matrix. Okay, and lastly, see, we already know what is the response at t is equal to 0. So at t is equal to 0, we know what is the value of u, we know the value of u dot, we know the value of u double dot. That is the, this is the displacement, velocity, and acceleration at t is equal to 0. But for calculations purpose, we should know what is the value of velocity, or what is the value of displacement at one step prior to this. Okay, because this will be required in the further calculation. So we need to know what is this. So for that purpose, we have one expression, that is u. Okay, so u at this is minus delta t. So this can be calculated by expression u, okay, at t is equal to 0. this will be known to us, okay, minus delta t into the velocity at t is equal to 0. Let me write down. I think this is into the velocity at t is equal to 0. Okay, then a3. Okay, this expression is already explained, and velocity or the acceleration at t is equal to 0. So this is u double dot at t is equal to 0. Okay, so here we can know what is the velocity, what is the displacement at t is equal to 0. So displacement at t is equal to 0 is already given to you. So this is already 0 over here. Okay, so you don't have to worry about that. The delta t value is minus 0.2. This we have already calculated. The velocity, that is u dot at t is equal to 0, this is already 0, so you don't have to worry about this one also. And a3 is 0.02 multiplied by the acceleration at t is equal to 0. So acceleration at t is equal to 0, here we have already calculated. Okay, so here we have already calculated, so this comes out to be 2. So the displacement at minus delta t comes out to be 2 into 0.02. So I think it is 0.04. Am I right? Barabar hai?
Yes, sir.
Yes, sir.
Okay, so so this completes the part 1. Okay, so in the part 1 we have calculated all the integration constants and the effective mass matrix and the displacement at t is equal to minus delta t. Okay, so now we are going for now part 2. So I am writing down over here part 2. So now in the part 2 I am going for the step 1. Okay, so in the step 1 I am going to calculate what is the displacement, velocity and acceleration at time is equal to delta t. Okay, so here what we have right now, we know what is the response of the structure at t is equal to 0. We know only the displacement at t is equal to minus delta t. Okay, so here we know what only displacement, here we know the displacement, velocity as well as acceleration. Okay, so this is the current situation which is there. So now we have to calculate the response of the structure at t is equal to plus delta t. This means we know we should calculate what is the displacement, what is the velocity and what is the acceleration at t is equal to delta t. Okay, so let's begin with that. Okay, so this is totally now unknown. Okay, so in order to proceed this, we have to first of all calculate the effective load vector. So effective load vector R can be calculated by a simple expression. Okay, so let me write down that expression. So this is R at t is equal to 0. So this is equals to R, okay, at t is equal to 0. Then we have minus, we have one bracket, then we have k. So this is your k matrix. Okay, then minus a2 into we have a mass matrix. Okay, and this has to be multiplied by the displacement at t is equal to 0. So this is the displacement, that is u at t is equal to 0. Okay, then minus we have a2 a0 into mass matrix. Okay, then we have a1 into c matrix, that is a1 into c matrix. Okay, multiplied by the the displacement at minus delta t. So this is the displacement at minus delta t. Okay, so now let us try let us substitute these values. So this r is the load vector, and this load vector is given to you in the numerical as this 8. Okay, this 8 is already given to you. Okay, so this load vector 8, it is not changing with time. For the time being it is constant, so I'm keeping this as 8. And we have k matrix. Okay, so k matrix is already there, so its value is 1. Okay, minus a2. So a2 we have calculated as 50. Okay, and mass matrix, that is m matrix, is already given to you as 4, okay, multiplied by the displacement at t is equal to 0. So displacement at t is equal to 0 is already given in the problem as 0. Okay, so this entire term becomes cancelled. Minus, we have a0. So a0 value is 25. Okay, so I'm putting it in a round bracket. The mass matrix is nothing but your 4. Okay, minus a1. So a1 value we have calculated as 2.5. Okay, and the damping matrix is the C matrix, and C matrix is given to you as 2. It's a 1 by 1 matrix. Okay, and then it has to be multiplied with the displacement at t is equal to minus delta t. Okay, so at t is equal to minus delta t, this we have already calculated over here. Okay, so this we have already calculated. So this has to be multiplied with 0.04. Okay, so now can someone tell me what is the effective load vector R now?
And 2.
Sorry,
0.2.
0.2. Please check your calculations. This is 8 minus. So this entire term will be 0. Okay, all you have to do is do this calculation part.
So 4.2.
4.2, right? Okay, so this is your 4.2. So this is the effective load vector for the first step. Okay, so every time this R is going to change. Okay, so this is the first step. So we are calculating the response as delta t, time is equal to delta t. So we have calculated the effective load vector R. So now we have to find out first of all what is the unknown displacement. Okay, so to calculate the unknown displacement, we have a simplified expression, that is effective mass matrix M multiplied by the displacement at now delta t, this is known to us, or this is unknown to us. Okay, multiplied by effective load vector R. Okay, so effective mass matrix we have already calculated in the initial calculations. So its value is 105. Okay, and this is nothing but the unknown displacement at delta t, and the effective load vector R is 4.2. Okay, so now can someone tell me what is the displacement? Yes, please, at delta t. 105 divided by 4.2. Or rather ulta, 4.2 divided by 105. How much is that?
0.04.
0.04. So 0.04. So here you see there are three unknowns. Okay, u double dot and u dot and u double dot over here. Out of this, now the velocity, or the unknown displacement part is now successfully calculated. Okay, so now we have to calculate the velocity as well as the acceleration. Okay, so in order to calculate the velocity, so velocity, let me go down slightly. Okay, so velocity is u dot term, and I want to calculate at delta t. Okay, so if you want to calculate this, so what expression you have to use is this one, that is a1. Okay, so we have a1 multiplied by the displacement which just now we have calculated, that is u. Okay, at delta t, so this is we have just now calculated. Okay, minus the displacement at one step prior, so this is the u at minus delta t. Okay, so both the values are available with us. Okay, so the a1 value is 2.5. Okay, multiplied by the displacement at t is equal to delta t, that is 0.04, just now we have calculated. Okay, minus the displacement at one step prior, so this also we have calculated as 0.04. Okay, if you remember this, so 0.04 negative here we have calculated. Okay, here we have calculated this. Okay, so this is there. So ultimately the velocity term, okay, so this term becomes 0 because this is going to cancel each other. So the velocity at delta t is going to become 0. So basically this term, the velocity term, is now also calculated. Okay, now let us go for the another unknown, that is the uh, acceleration. So to calculate the acceleration, that is u double dot at delta t. Okay, so what expression you will be using is this one. Okay, so we have a expression like a0 multiplied by, we have the velocity or the displacement at minus delta t. So this is the displacement at minus delta t minus 2 times. Okay, minus 2 times we have the displacement at 0. Okay, and we have the displacement at the current time. So it should be plus, not this one, and the displacement at delta t. Okay, so all three displacement, that is at minus, then 0 and plus, both are there in this expression. So if you substitute these values, so this comes out to be 25. The displacement at minus delta t, just now we have seen it is 0.04. Okay, this is minus 2 times the displacement is already 0 in the initial stage, and this is 0.04. This also we have seen. Okay, so now with this you can now calculate what is the acceleration at delta t. So can someone give me this value, please? Yes, anybody?
Sir, 2.
Yeah, it is 2. Okay, so this value is now 2. Okay, so now if I draw a chart kind of a thing, okay, so if I enter a table over here, okay, so if say this is my time, so this is time. Let me increase the font so that it will be visible to you. Okay, so this is, we have time, and let us say this is u, and this is u, say dot, I'm just writing ud. Okay, and say u double dot. Okay, and put a dot sign over here. Okay, so right now what is available with this minus delta t. Here we have 0, and here we have now t. Okay, so what we have calculated just now is the response at this point. So velocity, acceleration, and displacement we have calculated. So the acceleration is coming out to be 2. Okay, the velocity is coming out to be 0. Okay, and the displacement is coming out to be 0.04. Okay, at this point everything was known to us, or rather we have calculated also. So if you refer this, the velocity and displacement, they were 0, but acceleration we have calculated as 2. So the acceleration was 2, and this is 0, and this is also 0. The velocity, the displacement at delta t minus, so this also we have calculated, and this was not required. Okay, so this is the situation, current situation. So now what we have to do is we have to go for the one more, you can say, trial after this, or one more cycle after this, so that we can get the values of the displacement, velocity, and acceleration at 2 times delta t. Okay, so can you do that please? सब लोग करो तो जरा, एक साइकिल और करो आगे. So here we have 2 delta t. So this is dt, not t. Okay, so I want to calculate this. So for this purpose, now you have to go for the one more step. So here, let me write down. Okay, so here we have to go for step 2. Okay, so now in this step 2, what we have to do is, first of all, we have to calculate the effective load vector R. Okay, so here effective load vector R is need to be calculated. Okay, so let me write down an expression for this. Okay, so this R can be calculated as the load vector R at t is equal to 0. Okay, then we have minus, we have K matrix. Okay, then minus A2 into M, that is the mass matrix, multiplied by the time will be now increased by delta t. Okay, so now you will have here something like u at delta t. So if you refer this expression here, this is t is equal to 0. Can you see this? This is 0, but now this will be now delta t. Okay, then we'll have one more the equation will continue. So this equation is something like a0 into m, okay, minus a1 into c, multiplied by, now you will have the displacement at t is equal to 0. So earlier if you
Sir,
see,
R में
it is at minus
why-
t, है ना? So now here it will be 0. Everything is added with delta t now. So all the values are known to you. So please give me the effective load vector R for this.
R के केस में अपन डेल्टा टी क्यों नहीं किया?
R is changing, it is not changing with time, it is given in the problem, so it will be taken as constant.
Okay.
So if it is changing with the time, so if you refer the this problem over here, so this R value, it is constant. Okay, so it is not changing with time. If it is changing with time, you will get a table wherein you will find what is the value of R when t is equal to 1 second, 2 second, 3 seconds, like that. Okay, that's why it is taken as constant. Okay, now please tell me the effective load vector R, please. कितना आ रहा है?
Sir, 15.96.
Yes, 15.96. 15.96. Okay, so this is the first thing. Then now we have to start calculating the unknown displacement, unknown velocities, and unknown acceleration. Okay, so now unknown displacement, it can be calculated by a simple expression. So this is the effective mass matrix. This already we have calculated in the initial calculations, multiplied by, now u will be now 2 times delta t. Okay, equals to your effective load vector R. Okay, so can you do these calculations, please? So this value is 105, I suppose, and u into 2 times delta t, and this R value is 15.96. कितना आ रहा है डिस्प्लेसमेंट?
0.152.
एक मिनट, हाँ. So u at 2 delta t is
152.
0.152. Okay, so here you see this value is 0.152. So now in the table I can write the unknown displacement as 0.152. Okay, so now you see our table is now started building. Okay, so now the displacements are now known, so now I can easily calculate the velocities and accelerations. Okay, so in order to calculate the velocity, so I am just going to write down the expression. So now this will be the velocity at 2 times delta t. So this can be calculated by a simple expression. So this is nothing but a1 into, okay, so this will be the displacement at 2 times delta t, okay, minus the displacement at 0. Okay, so if you refer the earlier expression, so here this was the expression, so here you can see that this is u at delta t and u at minus delta t. So everywhere if you add delta t, so it is going to become u at delta 2 times delta t, and this will be u at 0. So all the values are known to you. So you can easily get the velocity at 2 times delta t. Can somebody tell me the values, please?
0.28.
0.28 or 38? Please check. 0.38. Okay, so this is the velocity. So I am going to write down over here 0.38. Okay, so now similarly, now you can calculate the acceleration also. So this is the acceleration at 2 times delta t. Okay, so this acceleration equation will be something like this one. That will be a0. Okay, so let me write down. So this will be a0 into u at 0. Okay, minus 2 times u at delta t. Okay, plus u at 2 times delta t. Okay, so can somebody tell me this values, please? Again, you can refer this expression with the earlier one. So here it was minus delta t, 0 and delta t. So everywhere if you add delta t, so this will become 0, this will become delta t, and this will become 2 delta t. That's what I have written over here. 0 delta t and 2 delta t. All the values you have to take from this table. So the velocity at 0 is 0. Okay, the displacement at 0 is 0 over here, and then at delta t it is 0.04, and at 2 delta t it is 0.152. So how much is this acceleration?
1.8.
1.8. Very good. 1.8. So this becomes now 1.8. Okay, so this is how you have to solve this for 5 number of steps, because you see in the numerical it has been asked that you have to solve this for 5 steps. Okay, or rather it has asked for 12 steps, not for 5 steps, 12 steps. So we won't be doing 12 steps, so don't worry, but I want all of you to find out the values for one more cycle. Okay, so can you do this? So this is 3 times delta t now. So you just have to repeat each and everything one more time. So the stepwise calculations you have to repeat, and then you can get these values. Okay. So please do this. Meanwhile, I'll just take your attendance part. Okay. So everybody, please follow this. Please start doing calculations. Roll number 3 is present. Structural engineering, I think she is not there. 4, 5, 6, 7, 8, 9, 10. Roll number 11. Okay. Okay, geotech students, I think you are not writing your roll numbers. I think all 10 are present today. Geotech students.
Yes, sir.
Good. Yes, anybody got the answers, please? किसी का इफेक्टिव लोड वेक्टर आया क्या? Anybody? Yes, anybody, please? Answers?
Sir, R 34.648.
Sorry?
34.648 R.
34.648. Okay, continue. आगे का चेक करो.
Sir, U 3 delta T is 0.329 or 0.33.
0.329. Yeah, okay, that's correct.
0.33.
Yeah, 0.329 you can keep, no issue.
Okay.
0.329. Okay. Give me the value of velocity as well as acceleration. Yes, somebody?
0.722.
0.
723.
Yeah, correct. 0.72. And the acceleration? आ गया?
2.55.
नहीं. Incorrect.
2.625.
No, it is 1.6 something.
सर एक एक डेल्टा टी ऐड करना पड़ेगा ना.
हाँ हाँ, सब में है. इसमें ये जो एक्सप्रेशन है, so you can see it on the screen. So here you will get delta t, here you will get 2 delta t, and here you are going to get 3 delta t. So everywhere you have to add delta t for every step.
So 1.675.
Yeah, 1.6 something is there. Okay, so I think that should do. Okay, so I think I should stop now. I hope you have understood the method. So you can follow the same process for another increment, that is 4 delta t, 5 delta t, and so on. Everything will remain same except the equations, they will also remain same. Only thing is the delta t term will be increased by one more delta t with the every step. Okay, so this is the only difference. Okay, so this is all from my side. So let me stop the recording now.